Underneath the clean interfaces of our devices, the physical network connecting them is hostile. There are no dedicated lanes or guaranteed clear pathways. Millions of data streams are constantly competing for space, colliding and diverting in real time across overloaded routers and degraded wires. This animation maps the 4 physical threats data faces as it navigates this environment. A packet of information can get delayed in traffic, network hardware can accidentally duplicate it, electrical interference can corrupt its internal contents, or a connection can simply drop, causing the packet to vanish into a state of loss. A single missing or corrupted packet creates an unfillable gap, rendering a downloaded image unreadable or an email completely scrambled. So if we take a single piece of data, our protagonist packet, carrying a vital fragment of a larger message, we have to ask how it manages to traverse this chaos and arrive intact. The network itself offers no guarantees of safety. This invisible mathematical layer of logic sits directly on top of the physical chaos, providing a protocol designed to anticipate failure and systematically correct it. The first protective mechanism is identity. Before any packet leaves the sender, it is permanently stamped with a sequence number. It joins a queue, explicitly numbered 1, 2, 3, and so on, before heading into the unpredictable network. This numerical identity detaches the data's order from the physical reality of its travel. Even if packet 3 takes a faster route and physically arrives before packet 2, the sequence number provides the exact blueprint needed to rebuild the original structure. Once the packet arrives, it triggers the second mechanism, an immediate response. The receiver absorbs the data and fires back a tiny, distinct green signal called an acknowledgement. When that token reaches the sender, it updates a status board, confirming that specific sequence number has safely crossed the gap. This alternating rhythm of outgoing data and incoming acknowledgements forms a constant feedback loop. It runs quietly beneath every digital interaction, confirming each piece of data one by one. Without this continuous loop of confirmation, a sender would simply be transmitting data blindly into the network, completely unable to verify if any of it actually survived the trip. That brings us to the core problem of a lost packet. When a piece of data vanishes due to a dropped connection, the network does not generate an error message to notify the sender. The packet simply ceases to exist, leaving the sender waiting for a reply that will never come. To solve this, the sender uses a timeout mechanism. The millisecond a packet is transmitted, an internal countdown clock begins. If the timer expires before an acknowledgement returns, the sender makes a calculated assumption that the packet is dead. It immediately generates and sends a fresh, identical copy of that missing sequence number. Tuning that exact countdown duration is a highly specific engineering challenge, as illustrated in this 3-panel breakdown. The sender has to guess exactly how long a normal round trip should take, and calibrating that timer requires a strict balance. If the timer is set too long, the system sits idle during a real loss, stalling the entire transfer. But if the timer is too short, the sender panics early. It assumes a packet is lost when it is merely delayed in traffic, generating an unnecessary duplicate copy and clogging the network with redundant data. By utilizing the timer, the system treats the absence of a response as actionable data. Silence triggers a resend, allowing the protocol to repair its own gaps entirely automatically. On the other side of the connection, the receiver is equipped to handle the chaos. When sequence numbers arrive out of order, the receiver places the early arrivals into a temporary holding buffer. They wait there suspended until the delayed packet finally shows up, allowing everything to snap neatly into the correct sequential alignment. The receiver is also watching for those accidental duplicates caused by aggressive timeouts. It checks the sequence number, recognizes that it already possesses that exact piece of data, and quietly drops the clone into a discard pile so the final file isn't corrupted by repeated information. But the final physical threat is more deceptive. Sometimes a packet arrives perfectly on time, with the correct sequence number, but an electrical spike along the wire has scrambled the actual data hidden inside. To catch this, the receiver performs an integrity scan. It uses an embedded mathematical formula called a checksum to calculate a fingerprint of the packet's contents. If the calculated math does not match the packet's attached fingerprint, the receiver knows the data is corrupted and immediately discards it. Crucially, the receiver does not send an acknowledgement for the corrupted packet. By deliberately staying silent, it forces the sender's timeout timer to expire, triggering a clean retransmission of the data. The result of this exhaustive filtering process is total accuracy. Every packet has been accounted for, sorted, verified, and merged. A chaotic, unreliable physical journey concludes with the flawless reconstruction of the original data. However, this level of strict verification is a choice, mapped out in this two-column comparison. On the left is reliable transmission, used for file downloads and emails. On the right is best effort transmission, used for real-time video calls and live gaming. Guaranteeing perfect accuracy costs time. Every timeout, retransmission, and sorting delay pauses the flow of data. For a live stream, waiting for a retransmission would cause the video to freeze continuously. Instead, best effort transmission skips the acknowledgements and accepts minor glitches or visual gaps to keep the feed moving smoothly. It's worth noting these integrity checks only protect against random environmental errors, like degraded cables. They cannot detect a malicious actor deliberately altering data and recalculating the checksum, which is why secure connections require separate cryptographic layers on top of this process. Yet, for the vast majority of our daily digital infrastructure, this precise sequence of tagging, confirming, timing, and scanning happens constantly. Billions of packets execute this survival loop every single second across millions of connections worldwide. The Internet's pervasive reliability is grounded in a rigid set of rules, a mathematical agreement to number, verify, and correct each piece of data, creating a trusted structure out of an inherently chaotic environment.